Good morning. Welcome to our event today. My name is Sugata Sanyal. I'll be your host today. I am the founder and CEO of ZINFI Technologies. We provide an industry leading enterprise grade SaaS platform for enterprises. And I would like to take a moment to introduce our sponsor, Michael Murray. Michael is a senior account manager at Databank with over 17 years of experience in data center and cloud services. And Michael has worked previously at NTT Global Data Center and Computer Associates. So, Michael, welcome to our event, and I'll let you take it from here.
Morning, everybody. Thanks, Sugata, and all the alumni and friends of NJIT for welcoming me, taking time out to participate in today's event. I look forward to learning from our distinguished speaker today. A little background on Databank, formed in 2005. Our core business is the ownership and operation of physical data centers. We offer cloud services, bare metal services, and other managed services. Paul Atala, my counterpart, is an alumni from NJIT. Started collaborating with contacts back in 2022. Paul's previous relationship with the university made him aware of some potential data center needs. Currently, NJIT is a Databank HPC customer at our data center in Piscataway, New Jersey. HPC stands for High Performance Computing. HPC combines hardware, software, systems management, and data center facilities to support a large array of interconnected computers working cooperatively to perform a shared task, generally too complex for a single computer to complete alone. NJI infrastructure utilizes high power density cabinets reaching up to 85 kilowatts per cabinet. They use rear door cooling for these high density cabinets. Currently, Databank is providing the highly secure physical data center environment for their server cabinets and approximately 400 kilowatts of power. The HPC cluster that HJIT uses is called Wolver. These host a slew of research categories within the HPC cluster. Some of the examples are material science and engineering, robotics and machine intelligence, data center and management, environment and sustainability, bioscience and engineering. The cluster currently contains Dell HPC hardware. They are also currently adding NVIDIA hardware as well. They were selected by NVIDIA to be one of the first to use NVIDIA's GH200 Grace Hopper superchip. As a sidebar, Databank currently supports NVIDIA's GeForce Now gaming unit at 7 of our data centers in the US. Aside from traditional research, now they're diving into AI research and its possibilities. Paul has developed with Databank a great partnership with NJIT. We have a partnership with them, a one of a kind with Databank, where we have a scholarship program, an internship program, and an annual sponsorship gift. The sponsorship sponsoring this AI series is part of that partnership. Databank appreciates the partnership, and we look forward to continuing our relationship and partnership with NJIT. I'm pleased to introduce our distinguished speaker today, Dr. David A. Bader. Dr. Bader is a distinguished professor and the director of the Institute of Data Science, an IEEE, ACM, SIAM, and AAS fellow. He received the IEEE Sidney Fernbach Award and was inducted into the University of Maryland's Innovation Hall of Fame back in 2022. Dr. Bader has significantly contributed to high-performance computing, serving on the White House's NSCI panel and various NSF committees. He has over 188 million in research awards, over 300 publications, and an H-index of 66. He has directed critical AI and computing initiatives at Facebook, NVIDIA, and the Sony Toshiba IBM Center. Please join me in welcoming Dr. David A. Bader, who will speak next. Dr. Bader, the platform is yours.
Thank you, Michael, for that very kind introduction. And I'd also like to thank ZINFI CEO and founder Sugata Sanyal, who is also an NJIT alum, for hosting this podcast, and also to Databank, Raul Martinek, who's the CEO, and Paul Atala, our NJIT alum. Databank is the partner that provides the HPC data center for the New Jersey Institute of Technology. I'm very glad to be here today talking about two areas of high interest: artificial intelligence and high performance computing. So it's a lot of acronyms, AI and HPC, and I'm just very excited to be here today to talk about this. As was mentioned, I'm a distinguished professor and founder and director of NJIT's Institute for Data Science. I've been in the area of high performance computing now for many decades. And in fact, the awards that I've received, the IEEE Sidney Fernbach Award and being inducted into University of Maryland's Innovation Hall of Fame in the A. James Clark School of Engineering, were for my invention of the very first commodity Linux-based supercomputer. That's the model of computing that's used in all top supercomputers today. And I've also been able to innovate, for instance, using accelerators like NVIDIA GPUs and the IBM Cell Broadband Engine processor, among other chips that have given us the ability to do the large-scale artificial intelligence training and inference that's really been sweeping the world the last year or so. So at NJIT, I pulled a couple headlines from the news. Recently, U.S. News and World Report ranked us in the top 50 public universities. And just last year, the Wall Street Journal, in their College Pulse rankings, named NJIT the #2 public university in the U.S. And if we look at both public and private, we're ranked number 19. So this is quite an honor to see how NJIT is really ascending in all of these national polls. In computing, where I sit, our student enrollment has been steadily increasing by leaps and bounds. In the last couple of years, as you can see on this chart, our student enrollment has grown to this year having over 4,700 students in computing. This makes us the largest computing program in the New Jersey, New York, Connecticut, in our tri-state area, producing more than 1,000 computing students each year who graduate with degrees from NJIT. And our expected revenue increase in fiscal year 24 is increasing by over $10 million due to this enormous student growth. And what's fueling that is our new focus on data science and artificial intelligence that are really fueling many different sectors of the economy today. Everything from transportation to security to gaming and entertainment to fashion, the tech sector to food and agriculture. All of these areas require computing and this new emerging artificial intelligence. If I look at NJIT across all of our colleges, we have over 13,000 students, and computing now has become the largest college at NJIT, with over a third of the students at the university in computing, and about the same number in engineering as well. So we're very proud of this growth, and we're on this journey that we expect will continue as new areas of the economy open up for computing students to really create that next workforce for changing and impacting the world and the economy. So as I mentioned, in 2019, I moved to NJIT as the inaugural director and founder of our new Institute for Data Science. This institute has about 40 faculty across these colleges that are participating in our centers and the institute, working on real-world grand challenges that impact people and this planet. For instance, we have a center for big data that focuses on big data analytics systems and tools, and the cyber infrastructure needed to, for instance, do these large AI training and inference problems. We have a world-class cybersecurity research center that's recognized as a center of excellence by the National Security Agency, and faculty work on practical encryption technologies, privacy technologies, information assurance, and many other research areas. There's a medical informatics center called the Structural Analysis of Biomedical Ontologies Center, focused on medical informatics and doing work in collaboration with the National Institutes of Health and the National Cancer Institute. We have a thrust in fintech that looks at analytics for financial services and the insurance industry. And finally, we have a brand new center called the Center for AI Research, focused on machine learning and AI, that houses a number of our real-world technologies that we're developing and many industrial partnerships. So across all of these centers and thrusts, we work on problems that are real-world grand challenges, from urban sustainability, healthcare analytics. How do we provide trustworthy, free, and fair elections, insider threat detection in large organizations, protecting and making resilient infrastructure? How do we identify and give attribution to cyber attacks and defend against them? And also modeling disease outbreak and epidemic modeling, such as the recent COVID pandemic. So these are the types of problems, the hallmark of which are very complex problems that require faculty, researchers, students, and staff coming together to bring in domain expertise, computing expertise, data science expertise, and artificial intelligence to be able to work on large, complex problems that require data and computational science to transition these technologies into practice. Now, the rankings at NJIT are many. I have just a couple of them up on the slide. And to call one out, for instance, in our online master's degree in data science, Fortune magazine recently rated us number 4 in their ranking this past year. So we're very proud of all of these areas that NJIT has specialized in here in the computing area. And just recently, we launched a brand new master's and graduate certificate in artificial intelligence that has launched this year. And I encourage you to check out this degree. Now, let me shift gears a little bit. And by now, everyone's heard of large language models and ChatGPT and many of these new technologies that are emerging. We're at a point in history where the amount of change that we've seen in just a few months eclipses any other period in human history where change has happened this fast and this rapidly. We're now at a point where, with all of the data that exists on the internet and in repositories, all of the new machine learning models and training mechanisms, and the rich high-performance computing with accelerators such as those from NVIDIA GPUs, we now have the ability to create AI models that are approaching human capabilities. Now, these are very, very impressive. Many of you have probably tried ChatGPT from OpenAI or Gemini from Google and have tried to see what these can do. These models are just massive, massive models. They often take days or months even to train on massive supercomputers that often cost $1 billion or more. And they have parameters that get set through this training. So for instance, GPT-4 that's used in ChatGPT 4.0 has over 1.76 trillion parameters. Gemini Ultra has over 1.5 trillion parameters, and Claude 3 and Olympus have over 2 trillion parameters. And we're getting ready to see new models that are being trained now that may have even larger numbers of parameters. Those parameters are what store the learned information and create models that are used for inference, or for instance, answering our human natural language questions that we may ask to these large language models. And you may not have one of these models that you create or own, but there are many models from these on this chart: nano, extra small, small, medium, large. There are models of all different sizes that we can train on our data, whether it's our corporate data or whether it's massive data that we have in large internet scale repositories, to answer particular types of questions that are going to help us in our work, in our lives, and on this planet. So, for instance, if I look at large language models and where they're impacting, the small models may be able to do simple arithmetic, debugging of computer source code, or comprehending a piece of text that they have read, if you will. As we get to medium-sized models, they can now do some more sophisticated linguistics puzzles. They can create some simple movies. They can start to comprehend, like on the GRE exams. They can have a little bit of physical intuition, understanding a little bit about physics, maybe some logical deduction. But as we start getting to larger and larger models, for instance, large models can understand complex geometric shapes. They can do elementary math. They can have causal judgment, and so on. Now, the extra large models like GPT-4 and Gemini are now, as we see in the news, able to college-level exams and do quite well. They can self-critique themselves and reflect on what information they've provided. They can build whole applications, vertical stacks that ordinarily we had programmers doing. They can reason spatially. They're very, very creative. We've seen DALL-E and ChatGPT able to create some quite impressive things. And the next generation is going to move us even further. They're going to be able to, for instance, do some long horizon planning. They may be able to persuade others. They may be more aware of the situations that they're in. And we're getting into this regime that we've never been able to experience before, and at such a rapid growth. So if you're a company CEO or chief technology officer, and you're wondering what this means for my company, what I say is that it's an important time to take notice of these machine learning and AI models, because they're going to change every aspect of every business today, whether it's how we hire our workforce, whether it is how the workforce interacts with their computers, how do we program, how do we provide systems to customers, how do we innovate. All of that is going to have AI and machine learning integrated at every point within our companies. And we have to engage with this now because our competitors are. So it's an advantage to understand and unlock the abilities created by these LLMs. Now, where I work has, I like to explain it through this data quad. I work in spaces where we often have massive amounts of data, and we're trying to understand what sits in these data sets. So, for instance, in the lower left-hand quadrant, I've drawn axes where the x-axis is objects in the data, from known objects on the left to unknown objects on the right. And on the y-axis, I have patterns, from known patterns on the bottom to unknown patterns on the top. So this divides the space of data problems into these four quadrants. And if I go back to that lower left-hand quadrant where I have known objects and known patterns, a type of problem in this space may be one where you own a store and you create tables for the products that you're selling. You'll have SKU numbers and object descriptions. You'll have an inventory of account. And then for your customers, you'll have a table on each customer. Maybe you have their name, you have their email address, you have their mailing address, and so on. And every time a customer checks out, you create a new record that combines a customer with a set of items and quantities that they purchased. This type of data problem has been solved in the 1980s through relational databases, where we can ask questions about what objects, for instance, in my store do customers typically purchase together, or what are our sales trends and predictions. If I go to some of the off diagonals, like let's take the upper left, where I have known objects, but unknown patterns. A type of problem in this space, maybe you're so a type of problem in this space may be that you're the chief information security officer of a Fortune 1000 company, and you have a large workforce, and what you're monitoring for are insider threats. You're looking for individuals that may trip some security tripwires that you have in the company. They may access documents that they are not allowed to see. They may go to websites that are blocked or banned. And through all of these actions, what you want to decide as the CISO, is this like every ordinary human? Did they just make some mistake? Or are they up to no good? Are they in collusion with other employees? Are they looking to steal IP or have some detrimental effect on the business? So what I want to do is go to a known object, that individual, and then explore around them to understand the context in which they sit. This type of problem has been solved very well in the 1990s by vertical databases. They provided solutions in this space. If I go to the lower right quadrant, where I have known patterns but unknown objects, the hallmark of this type of problem is that I have some pattern, maybe it's a graph or a motif, and here I have an image from communications of the ACM inset, where I have a image of a pattern. Here I have two people, they live together. One is renting a truck, the other is buying fertilizer, they're observing a factory, and that may be a pattern that I'm monitoring for because they could be domestic terrorists trying to build a bomb. And then I have some observed data that I want to see. Do I see this pattern of badness somewhere in my observed data? And also, vertical databases and other technologies have been able to solve this problem of subgraph isomorphism or motif finding in large graphs. Now, the quadrant that really excites me, where I'm really interested, is this upper right-hand quadrant, the fourth quadrant, sometimes called the quadrant of unknown unknowns. Here, you may be an analyst in a company or organization, and you're handed a hard drive. Maybe you're given tens of terabytes of data. And what you're trying to do is reduce surprises within your organization. So you don't know what sits in that data. You don't know what types of surprises you're looking for. What are the threats within that data? What are the opportunities within that data? And so what I typically do in this space is try to take the objects that I find in the data and make them vertices, and take the relationships between those objects and make them edges in a graph. So I turn this into graph data science, where I have vertices and edges, much like a social network that connects the objects together. And with this, I move into a space called graph data science. And it often involves very large data sets. And the data typically isn't static. Typically, the data is coming to us in real time. We may get batch updates, for instance, in cybersecurity, coming every millisecond. We may have data dumps every hour, every day, every week or month. And so that means these graphs are dynamic, or they change in the face of this streaming data. So some great examples of these types of problems are in areas such as healthcare, trying to model the spread of disease, detect and prevent epidemics and pandemics like SARS-CoV-2 that we recently saw. Or maybe in massive social networks, where we're trying to understand communities. How do they form? How do they dissipate? What are their intentions? How do the populations change over time? And what happens during a pandemic spread among people? Or how do we model transportation and evacuation if we have a severe storm or weather event that is coming towards our town? In intelligence, we have business analytics, anomaly detection, security, as I talked about a few minutes ago. In systems biology, we want to understand complex life systems, do drug design, understand microbial research, even unravel the mysteries of the HIV virus and understand life itself. I mentioned trying to have a resilient power grid. We know electric power is responsible for our communication systems, transportation, energy, water, even our food supply. And when an electric power grid goes down, we may lose heating or cooling, and that impacts lives. It's a existential threat when we lose our power grid. And even modeling and simulation, performing full-scale economic, social, political simulations of entire nations as they react to new policies or new treaties that may be signed. So all of these problems require predicting and influencing change in real time and at this massive scale. And this is a place where graph data science, knowledge graphs, machine learning, and AI all come together to try to form solutions to solve these types of problems, many of which I work on in my lab. Now, we've been working for a couple of years now on a software framework that helps us work on these massive scale graph problems. We call the project Arachne, and it is an open source framework for interactive property graphs at scale. A property graph is like a social network where we have vertices and edges, but we have properties or attributes on both the vertices and edges. And these allow us to create very rich problems and abstractions from many of the real world problems that I've talked about. We're very fortunate to have support from the National Science Foundation that has been a strong supporter for this research that we're doing to democratize supercomputing and the ability for anyone on this planet to do large-scale data science and graph analytics through this framework that we've been creating. Now, in this framework, we are tying together productivity and performance. The lingua franca of data science today is the computer language, the programming language called Python, that probably everyone in this room and everyone on this live stream has used and knows how to program. Unfortunately, Python is not highly performant in large-scale problems, and here we rely on an open source compiler called Chapel, originally developed under a DARPA program about 25 years ago, called the DARPA HPCS, or High Productivity Computing Systems program, under the supercomputing company Cray. However, recently HPE acquired Cray, and this is now the HP Chapel programming language, supported by a fantastic team at HPE. And recently, Chapel version 2.0 was released that's also able to use both CPUs and GPUs to give us this productivity programming language and framework for everything from a laptop to a supercomputer, and to be able to allow anyone to program these different parallel and distributed computing systems. So I'll tell you in a minute how we combine Python with this Chapel programming language. And again, all of these components are open source. So here I have a picture of our framework. Arcuda is the base data science framework, and the Arcuda modules related to graphs are what we're calling Arachne. So this is really the Arcuda Arachne framework. And here we have a user on the left-hand side of this picture. They are interacting with their Jupyter notebook or a Python file, and they're interrogating their data sets. And they want to scale up from working on their laptop or their workstation to data sets that are tens of terabytes in size, but they don't want to learn high-performance computing and supercomputing. They want to be able to use the same tools and the language like Python that they're very comfortable with for doing these types of analyses. So what we provide and what we're building out at NJIT is on the right-hand side. There is a ZMQ, a zero message queue, that ties their Jupyter notebook to a Chapel server. Again, Chapel is this productivity and performance framework from HPE that can run on everything from a laptop to a cluster to a highly multi-core server, all the way to a big MPP or supercomputer. And the data, the large data, which could be tens of terabytes, and metadata sit on that server, and the user has the illusion of just running on their desktop. But this Chapel server could be anywhere in the world, and they're interacting in near real time with their Jupyter notebook, and may not even know that there's a supercomputer in the background powering their analytics and their graph queries. This has worked quite well and is used by a number of organizations for solving some of the most challenging large-scale data problems. We would love not to have to build this out. We'd love to pick up an enterprise class solution from Apache or AWS or Google, but unfortunately it just doesn't exist. There's no other tool that works on big data at the scale. And so we've built out this framework to be able to work in enterprise class organizations to solve some of these most demanding problems. Now, what excites me is that we are able to apply this framework to many, many problems in science and engineering. For instance, here's a project that we've recently been working on called the Connectome Project. And the slides and pictures here are courtesy of my collaborators at Harvard University, where they are now able to image brains, entire brains, down to the neurons and synapses. I'll show you a little fly through here of what these images look like. And we can, for the first time, have better understanding of how brains are organized down to the neuron level. And maybe we'll even make better AIs by having more power efficient and smaller models for training once we understand how these real brains work. And of course, we want to understand these brains so that we understand development in humans and understand aging and mental illness and other areas that are really, really important for understanding. We're at such an amazing period in time. For instance, in this image over here, this was recently put together by HHMI, Howard Hughes Medical Institute. And this is a full Drosophila brain. Drosophila is a fruit fly. And there are thousands upon thousands of neurons in this brain. Each one of them is colored. And for the first time, this is a full brain where every neuron has been identified. And as you see this visualization using tools that Harvard, our partner, has created, the neuroscientists are able to pull out different sections of these brains. For instance, the neurons involved with the optic networks, and you see them close to where the eyes are, or the sensory network in the fruit fly. Here, we're now highlighting visual projection, and so on. This is fantastic. We're getting new insights by being able to understand features down to the individual synapses that connect these neurons in the brain. Now, I don't know about you, but we're not as close to fruit flies as you would expect. So we hope to learn from some of these systems here, but we have a whiles to go until we start imaging humans to understand the brain structure in humans. Now, just to show you a picture, here's a neuron colored in blue, and we see axons and dendrites, which are these essentially these tentacle-like apparatus coming off of the base of the neuron that either send or receive signals through synapses on other neurons that they touch. So if I animate this slide here, you'll be able to see a fly-through as we zoom down into the synapses connecting two neurons together. And it's at this resolution, about 4 nanometers per voxel, that we can now image with our partners in the neuroscience committee, image these types of brains. Now, this is really, really challenging because even a portion of that Drosophila brain takes 1.4 petabytes. The H01 dataset that we have today is just massive in size. So for a petabyte dataset, we essentially need a petascale supercomputer to be able to hold it. Now, where we're excited by is that in about 3 or 4 years, we'll be able to have the images of a full mouse brain. That will take about an exabyte, equivalent to 1 million terabytes. Now, today we have a handful of exascale supercomputers that are emerging in some countries around the world. So possibly in the 3 or 4 years till we can sequence a full mouse brain, we'll have supercomputers that are able to hold and process those massive data sets. And I hope my Arachne and Arcuda software is able to provide the insights and queries that the neuroscientists need to understand how these brains work. Now, that mouse brain is going to be much more similar to a human brain than the fruit fly. And so in just 3 or 4 years' time, we're going to have revolutionary advances on the understanding of how these brains work and maybe how our own brains work. Here's an image of that HO1 or Drosophila fruit fly data set. It's 1.4 petabytes in size. There's about 57,000 neurons and about 133 million synapses or connections between those neurons. And if I map this to a property graph, that means I have a friendship network, if you will, of about 57,000 vertices, and there are about 133 million edges connecting those vertices together. So every vertex or neuron will have about a couple thousand other friends in this graph. And what we're trying to do is create tools so that the neuroscientists can find patterns or motifs that they're looking for in these data sets. The problem of motif finding is actually NP hard, but using our algorithms and heuristics and supercomputers, we're confident that we're able to create tools that are going to get us further and further along with understanding how these brains and eventually our own brains are configured and how they work and how they learn and recall and what happens during disease and aging and so on. So we're very, very excited. And again, kudos to our collaborators at Harvard University who are really the driving force behind the science that is getting us towards this ability to understand these incredible devices. So here's an example on the left of a motif query in a graph, and we're looking at neuron morphologs within the brain on the right. So this is the type of mapping that we're looking for. Now, if I switch gears, the ability to do this large-scale property graph analytics can apply to many areas. For instance, if I'm looking at understanding clinical patient records, for instance, with the adoption of the electronic health record system in many medical units, we can change clinical practices and understand more about patients. For instance, here, using community detection algorithms, we can find maybe family and generational patterns within clinical data of individuals in clinical settings. Or here, recently, we know from COVID that contact tracing was a massive problem, and we may need graph analytics like K-trust, triangle counting, triangle centrality, etc., to be able to understand how individuals are interacting with each other and maybe who we need to inoculate first with new immunizations, or where to break the contacts with the fewest number of individuals to make sure that we contain new emerging pandemics. Or in population health data, here we may start with tabular data that we load into Arcuda into very large data frames to analyze terabytes of tabular data, and then use Arachne and property graphs to build graphs out of these data frames and run graph analytics on this health data. So these are just some of the uses in health. Here's an example of the use that comes from cybersecurity. This is a place where we are very well integrated and working on problems with massive records and data sets related to cybersecurity. In this example, I have a data frame up top where every row is coming from NetFlow. This is the metadata attached to packets that are flowing around the internet. You may have a source IP address and port, and a destination IP address and port for every packet. Basically, that's the routing information of where it's coming from and where it's going to. And we may know what protocol is being used with that packet, how many bytes are in the packet, and many other characteristics of it. From this, we may form a large graph by taking the source address and making that a vertex in a graph, and the destination address and making that another vertex in the graph. And for every row in this massive data frame, we'll create an edge in the graph that represents that information flow, that packet going from the source to the destination. So this is an area where we've been able to use Arachne today and solve some very demanding cybersecurity problems that detect and give attribution to cyber attacks. They're able to build massive graphs in the order of minutes, and then the analyst may ask graph query questions through Arcuda and Arachne, and we can respond to those questions in mere seconds for some of the largest graphs in existence today. And this is just quite a phenomenal feat with this software to be able to do that. So I've told you today a little bit about Arachne, our large-scale graph analysis framework, and it extends Arcuda for productive graph analysis. Arachne is built on top of a novel sparse graph data structure. We have many innovations in the algorithms and the scalability that we achieve. We do the hard work of building out the internals so that users of Arachne and Arcuda get productivity by just interfacing through Python, and they don't have to understand all of the algorithms and the chapel coding that we do to make this work. All of the software that I talked about, including Chapel, are available open source on GitHub. I include the links here. Feel free to download it, or if you go to the Beers R Us repository on GitHub, you'll find tutorials, you'll find examples, you'll find slides, you'll find papers, you'll find documentation, a lot of materials that will help you get started, or you can reach out to us at NJIT, and we'd be glad to assist anyone who wants to try this out, kick the wheels, and see what they can do. Or if you're watching this live stream and you're a developer and you want to contribute to this project, by all means, we encourage developers to give back to the open source community. So much of what I talked about here today has been done with the support of my research group. I have research faculty like Dr. Zihui Du, a number of PhD students coming from diverse places, backgrounds, and interests, and they're just phenomenal and have contributed to many of the things that I talked about today. We also house high school interns. These are really, really fantastic students that may not have had as much college training yet in computing and data science, but are really, really innovative and have led to some of the breakthroughs that I talked about today. We also have both undergraduates and master's students as well who work in our labs and contribute to the successes that I talked about here. So they're phenomenal, and I love the job that I do as a distinguished professor because I'm able to work with such a fantastic set of people and students here. Now, finally, I want to plug a book that recently came out called Massive Graph Analytics. So if you want to learn and read more about this area, I encourage you to pick up a copy. All the royalties from this book don't go to me. They go to support students, and they go to really make the community better. And so I get no profit by doing this book. This was a project of love where I was able to bring together a number of researchers to create 21 chapters spanning algorithms, applications, models, frameworks, and software to really tell you about the state of the art in this space of massive graph analytics. And I collected over 85 contributors to the chapters in this massive book, and encourage you to pick it up if you want to learn more about this research space. So again, thank you for your attention and for joining this podcast and live stream. I have just really enjoyed being here and telling you all about the work that we're doing at NJIT. Again, I want to thank ZINFI and also Databank for their huge support of NJIT and this area, and look forward to interacting with you in the future. So thanks again for attending, and I look forward to seeing you soon. Take care.